In this video, I'm going to look at surface integrals on explicitly defined surfaces. First, let's talk about what an explicitly defined surface is. If I have a smooth surface S, it may not always be possible or necessary to define it parametrically. Surfaces that have the form z is equal to g of xy over a region R in the xy plane are explicitly defined in terms of x and y. We can continue to treat these functions as if they are parametrized simply by defining u is equal to x and v is equal to y. Making these substitutions in our tangent vectors t sub u and t sub v, we find that t sub u is equal to a vector with components 1, 0, and z sub x, and t sub v is a vector with components 0, 1, z sub y. The unit normal vector is a scalar multiple of n is equal to the cross product of t sub u crossed with t sub v, which is equal to a vector with components negative z sub x, negative z sub y, and 1, so that my magnitude of my cross product of t sub u crossed with t sub v is the square root of z sub x squared plus z sub y squared plus 1. Now that we have these tools in our toolkit, we're ready to construct our double integral for an explicitly defined surface. We're going to let f be a continuous function on a smooth surface S given by z is equal to g of xy for x, y in a region R. The surface integral f over s is given by the double integral over the surface of f of xyz ds is equal to the double integral over the region of f of x, y, and g of xy times the magnitude of t sub u crossed with t sub v, which is the square root of z sub x squared plus z sub y squared plus 1 dA. If my function f of xyz is equal to 1, the surface integral will give me the area of my surface. So let's work an example. I want to find the area of the paraboloid given by z is equal to 2 times the quantity x squared plus y squared, where 0 is less than or equal to z, which is less than or equal to 8, using an explicit description of my surface. If I use 2 times x squared plus y squared is equal to z, I get z sub x is equal to 4x and z sub y is equal to 4y. The parabola sits over x squared plus y squared is equal to 4, so that my r is equal to 2. Therefore, my double integral over the surface of 1 ds is equal to a double integral over the region of 1 times the square root of 16x squared plus 16y squared plus 1 dA. I can rewrite this as the iterated integral from 0 to 2 pi of the integral from 0 to 2 of r times the square root of 16r squared plus 1 dr d theta. The inner integral becomes 65 times the square root of 65 minus 1 divided by 48, so that my outer integral is given by the integral from 0 to 2 pi of 65 times the square root of 65 minus 1 over 48 d theta. When I evaluate this integral, I get the quantity 65 times the square root of 65 minus 1 times pi, all divided by 24. I want to work another example. I want to evaluate the surface integral that is given by the double integral over S of f ds using an explicit description for the surface f of xyz is equal to e to the z, where S is the plane given by z is equal to 8 minus x minus 2y. Using z is equal to 8 minus x minus 2y, I get z sub x is equal to negative 1, z sub y is equal to negative 2, and the limits of my integration will be from 0 to 4 on y and from 0 to 8 minus 2y on x. My double integral over the surface of f of xyz ds is equal to the double integral over r of e to the z times the square root of 1 plus 4 plus 1 dA. I can express this as the iterated integral from 0 to 4 of the integral from 0 to 8 minus 2y of the square root of 6 times e to the 8 minus x minus 2y dx dy. My square root of 6 is a constant and it comes out of my integration. And my inner integral gives me negative e to the 8 minus 2y minus 1. And my outer integral becomes the square root of 6 times the integral from 0 to 4 of negative e to the 8 minus 2y minus 1 dy. Completing this integration, I get the square root of 6 times the quantity e to the 8th minus 9 divided by 2. Here's a third example. I want to find the average value of the temperature function T of xyz is equal to 100 minus 25z on the cone given by the equation z squared is equal to x squared plus y squared, where 0 is less than or equal to z, which is less than or equal to 2. Using z squared is equal to x squared plus y squared, we get z is equal to the square root of x squared plus y squared. This means that z sub x is given by x over the square root of x squared plus y squared, or it can be more easily expressed as x over z. Z sub y, in a similar fashion, becomes y over z. The cone itself sets over the circle given by x squared plus y squared is equal to 4. The square root of z sub x squared plus z sub y squared plus 1 becomes the square root of x squared plus y squared over z squared plus 1, which is equal to the square root of 2. The area of my cone is given by the double integral over the surface of 1 ds, which is the double integral over r of 1 times the square root of 2 dA. I can write that as an iterated integral from 0 to 2 pi of the integral from 0 to 2 of r times the square root of 2 dr d theta. This gives me 4 pi times the square root of 2 for the area of my cone. The integral of t of xyz is going to be given by the double integral over s of the quantity 100 minus 25z ds, which is equal to the double integral over r of the square root of 2 times the quantity 100 minus 25 times the square root of x squared plus y squared dA. This can be written as an iterated integral where I have the square root of 2 times the integral from 0 to 2 pi of the integral from 0 to 2 of r times the quantity 100 minus 25r dr d theta. I complete the integration on the inner integral and I get the square root of 2 times the integral from 0 to 2 pi of 400 over 3 d theta. This gives me 800 pi times the square root of 2 over 3. The average value is given by dividing this by the area. So I take 1 over the area times 800 pi times the square root of 2 over 3, which is equal to 1 over 4 pi times the square root of 2 times 800 pi times the square root of 2 over 3, and I get 200 over 3. You'll notice that I had to compute my area first, and then I was able to finish finding my average value. Now you get to try it. Pause the video and find the average squared distance between the origin and the points on the paraboloid given by the equation z is equal to 4 minus x squared minus y squared, where 0 is less than or equal to z, which is less than or equal to 2. When you're ready, restart the video to check your understanding. I have an explicitly defined description for my curve, and I'm going to use z is equal to 4 minus x squared minus y squared to get z sub x is equal to negative 2x and z sub y is equal to negative 2y. My paraboloid sits over a circle given by the equation x squared plus y squared is equal to 4. The square root of z sub x squared plus z sub y squared plus 1 is equal to the square root of 4x squared plus 4y squared plus 1, which can be abbreviated using r squared in place of the sum of x squared plus y squared, so that I get the square root of 4 times r squared plus 1. The area of my paraboloid is given by the double integral over s of 1 ds, which is equal to the double integral over r of the square root of 4r squared plus 1 dA. I can write this as an iterated integral, the integral from 0 to 2 pi of the integral from 0 to 2 of r times the square root of 4r squared plus 1 dr d theta. Computing the inner integral and plugging it into my outer integral gives me an outer integral from 0 to 2 pi of the quantity 17 times the square root of 17 minus 1 over 4 d theta. I complete that integration and I find that the area of my paraboloid is given by the quantity 17 times the square root of 17 minus 1 times pi divided by 2. Now I'm going to compute the integral of the average distance from the origin. This is given by the double integral over s of the quantity x squared plus y squared plus z squared ds, which is equal to the double integral over r of the quantity x squared plus y squared plus the quantity 4 minus x squared minus y squared squared times the square root of 4x squared plus 4y squared plus 1 dA. Again, I'm going to make a substitution of r squared for x squared plus y squared. This allows me to write this as an iterated integral from 0 to 2 pi of the integral from 0 to 2 of r times the quantity r squared plus the quantity 4 minus r squared squared times the square root of 4r squared plus 1 dr d theta. I compute my inner integral, and I get the outer integral is equal to the integral from 0 to 2 pi of the quantity 4r squared plus 1 to the 3/2 power times the quantity r to the 4th minus 10r squared plus 39 divided by 28 evaluated from 0 to 2 d theta, so that my outer integral becomes the integral from 0 to 2 pi of 255 times the square root of 17 minus 39 all divided by 28 d theta. I complete that integration piece and I get the quantity 255 times the square root of 17 minus 39 all times pi divided by 14. My average value will take this integration value and divide it by my area. I'm going to get 2 over 17 times square root of 17 minus 1 times pi times the quantity 255 times the square root of 17 minus 39 times pi over 14. Canceling similar terms gives me a quantity 255 times the square root of 17 minus 39 over the quantity 17 times the square root of 17 minus 1. This is my average value of the squared distance between the origin and the points on the paraboloid for the paraboloid I was given when z lies between 0 and 2. This is how I can compute surface integrals when my surfaces are explicitly defined. Let me know if you have any questions.